Hello, and thanks for your interest in the fascinating and challenging subject of machinery alignment. This is the introductory tutorial and will discuss all of the very basic information you should be aware of prior to working on, monitoring, or operating rotating machinery. This information is intended for trades personnel, maintenance supervisors, vibration analysts, engineers, maintenance managers, and operations personnel. It will cover some very basic but vitally important concepts that will hopefully provide a good understanding of how rotating machinery works, what mechanisms destroy our equipment, and what we can do to ensure long-term survivability of our machinery. The major topics that will be covered include the 4 key ingredients to successfully align machinery, the symptoms you will see if machinery is subjected to run under a misalignment condition, some basic design principles of rotating shafts and the bearings that support them, and the types of static and dynamic forces that occur in machinery. With just about every difficult or challenging task, there are 4 key elements that will ensure success: training, tools, time, and inspiration. Take any one of these elements out of the picture, and there is a good chance that whatever it is you're trying to do, there is a possibility of encountering some problems or, worse yet, totally fail. Probably the first thing that crosses someone's mind is, why bother with alignment? Isn't the job of the flexible coupling to accommodate a misalignment condition? What's going to happen if we run machinery misaligned? Who should be held accountable for ensuring that all the drive systems are aligned properly? Well, the trades personnel, such as mechanics, electricians, and pipe fitters, are the ones who ultimately measure and correct the misalignment condition. But I also think that their immediate supervisor needs to have a good understanding of alignment just in case the tradespeople run into a problem. That supervisor should have enough knowledge and experience to assist in resolving whatever issues come up. Vibration analysts should also have a decent understanding of alignment since they are tasked with detecting this problem, yet many of them have never aligned a piece of machinery in their lives. They are also surprised to discover that much of what is believed to occur in machinery concerning vibration is not correct or misleading at best. Engineers are responsible for specifying what rotating machinery would be selected for the process, what type of flexible coupling will be used, the design of the foundation, base plate, and grouting, directing the efforts to discover how the machinery is moving from offline to running conditions, what the desired offline shaft positions should be along with the corresponding dial indicator or laser target values, conducting root cause failure analysis when shafts, seals, bearings, and couplings fail, and provide all of the technical direction, record keeping, and training for the rest of the plant personnel. The managers have the responsibility of providing the funding and the time for the required tools or training and the inspirational leadership to convey the message that accurate alignment is financially beneficial to the company. A common misconception is that once you align a piece of rotating machinery, it stays aligned forever. If you did annual alignment checks, you might be surprised to learn how many drive systems drift out of alignment. You know, perfect alignment in the real world is virtually impossible to achieve. It is important to understand what is an acceptable amount of misalignment and the difference between coupling tolerances and alignment tolerances. When you hear about alignment tools, usually the first thing that comes to mind are alignment measuring tools like dial indicators and laser detector systems. Indeed, these devices are critical, but dial indicators or lasers have never actually aligned any piece of machinery. All they do is measure the amount of misalignment. If a drive system is found to be out of alignment, you are going to have to use other types of tools to loosen foot bolts, safely lift machines to add or remove shim stock from under the feet, and precisely move a piece of machinery sideways or axially to correct a misalignment problem. Additionally, many people are unaware of the fact that certain types of drive systems should be intentionally misaligned. Once machinery is started, heat generated from friction in the bearings or heat generated from compressions of gases or from pumping hot process fluids, and the expansion or contraction of attached piping, ductwork, or frames, and concrete foundations will have a tendency to move the shafts to some other position than where they were at when offline. This phenomena is often referred to as thermal growth or hot and cold alignment. The most accurate way of describing this is simply offline to running machinery movement. The terms hot and cold and thermal imply that the only thing that causes machinery to move is some sort of temperature change in the machine. Indeed, temperature changes in the machinery are the primary cause for the movement, but other factors such as reactionary moments from a spinning rotor or operational piping strain can cause this movement. The term growth implies that machinery can only move in the upward direction when, in fact, machinery can move downward, sideways, and axially. Be aware that the tools used to measure the misalignment when the machines are not running are not the same tools you would use to measure how the equipment is moving from offline to running condition. Probably the number one complaint I hear from people in industry is that they are not given enough time to do the job right. Alignment shouldn't be a race against time. Successful machinery installation encompasses more than just measuring the positions of the shafts, moving machinery around, and bolting it down. I very rarely hear true professionals bragging about how fast they can perform open heart surgery, how fast new brakes are installed in a car, how quickly they can get their customers out of the restaurant, or how fast they can build a house. The issue of adequate time also encompasses the time needed to train personnel on how to do this correctly and all that is involved in this process. Industry assumes that the people they hire learned how to do machinery installation and shaft alignment before they started working there. Can anyone tell me if this is taught in high schools or colleges? No, it's not. I often hear that industry can't afford to take their key personnel away from their job long enough to attend a 2 or 3 day training course. In the long run, you can't afford not to. All of the training received or tools purchased or time allocated will go to waste if you do not possess the ambition and inspiration to want to do this correctly. It's easy to say that shaft alignment is extremely important and needs to be done properly as long as I don't have to do it. Of all 4 ingredients, training, tools, time, and inspiration, without a doubt, this is the most important one. Before we get into the more technical aspects of aligning machinery, let's take a look at what some of the symptoms of shaft misalignment are. One of the symptoms is that you will see premature bearing, seal, shaft, or coupling failures. First, we should talk about some very basic design principles of rotating machinery, starting with the rotating shaft and the bearings that support it. Shown here is a rotor from a steam turbine. A rotor consists of a shaft and rotating parts attached to it like blading or impellers or an armature. One of the basic design principles for a rotating shaft to be stable, it must have 2 radial bearings. Radial bearings maintain the center line of the shaft on a fixed axis of rotation. A thrust bearing prevents the shaft from moving in an axial direction so the rotating part doesn't touch a stationary part in the machine. There are two types of bearings typically used in rotating machinery: sliding bearings and rolling element bearings. The oldest bearing known to man is a sliding type bearing. In its simplest form, a rotating shaft is supported in a hollow cylinder riding on a thin film of lubricant. As the shaft rotates, a wedge of oil forms between the shaft and bearing, lifting the shaft upward. Once the oil wedge is formed, the shaft typically moves to one side and does not run in the exact center of the bearing. The minimum oil film thickness occurs at a line drawn through the shaft and bearing center lines called the shaft attitude angle. The minimum oil film thickness can range from 3/10,000ths of an inch to 2/1000ths of an inch or more. This oil film acts as a damping medium for small amounts of oscillatory shaft motion to occur. This oscillatory motion is what we refer to as vibration. Other common names for this type of bearing are journal bearings, plain bearings, Babbitt bearings, sleeve bearings, bushings, and tilt pad bearings. These types of bearings require a certain amount of clearance between the shaft and the bore of the bearing, often referred to as the radial bearing clearance. This clearance typically ranges between 3/4 of a mil to 2 mils per inch of shaft diameter. 1 mil is equal to 1/1000th of an inch. Incidentally, the term mil is also used as a unit of vibration measurement which quantifies the amount of oscillatory movement of a shaft inside the bearing or the amount of oscillatory movement of a bearing housing. There are several different methods to measure radial bearing clearance. One method is to use a product called Plastigauge. Plastigauge are pliable strands that can be purchased to measure gaps from 1 to 70 mils and comes in 6 different sizes for different gap measurement ranges. For radial bearings, the upper bearing half is removed, a piece of Plastigauge is placed on top of the shaft, the upper half of the bearing put into position and bolted tightly, then the bolts are loosened and removed, and the upper half removed again to observe how much the Plastigauge got crushed. The smaller the clearance, the wider the Plastigauge was flattened. You then use a gauge supplied with the Plastigauge to determine what the clearance was. Another method is to place a dial indicator on top of the shaft and anchor it to the bearing or machine housing. Then, lift up in the shaft and observe the amount of movement on the dial indicator. Actually, it's recommended to use both Plastigauge and a dial indicator because it's possible that the bearing assembly could be loose in its housing. The Plastigauge would tell you the radial bearing clearance, and the dial indicator would tell you the radial bearing clearance and the amount of bearing assembly to housing looseness. In addition to radial bearing clearance checks, you should also look for a tilt or twist problem in a bearing. Here is a photograph of a fan shaft supported in 2 separate pillow block self-aligning journal bearings. The upper bearing half on the inboard or coupling end bearing has been removed to check for bearing clearance and a tilt or twist condition. For bearings supporting a shaft in the horizontal position, a tilt condition exists when the center line of rotation of the fan shaft and the center line of rotation of the bore of the bearing are not collinear in the axial and vertical directions. To measure a tilt condition, remove the upper half of the bearing. Install the appropriate type of Plastigauge on top of the shaft and ensure the Plastigauge is long enough to span the full width of the bearing. Carefully place the upper bearing half back onto the lower half and tighten the bolts. Loosen and remove the bolts and remove the upper bearing half. Once you crush the Plastigauge and remove the upper bearing half, observe the clearance at both ends of the bearing. Use the crush gauge on the Plastigauge package to determine what the clearance is at both ends of the bearing as shown in the photographs. If the measured gaps at both ends are different, there is possibly a tilt condition present. For bearings supporting a shaft in the horizontal position, a twist condition exists when the center line of rotation of the shaft and the center line of the bore of the bearing are not collinear in the axial and lateral directions. A twist condition is measured using feeler gauges comparing the gap measurements at the four corners of the bearing as shown in the drawing and the photographs. If the gaps at the four corners are not the same, then a twist condition exists. Finding a tilt or twist condition is relatively easy. Determining what is causing it and what is required to correct it is far more difficult. Bear in mind that a tilt and twist condition can exist on machinery where the inboard and outboard bearings are held by a common housing like an electric motor. During outages, it is a common practice to remove the bearings and inspect them for damage or wear. Here is an example of normal wear on the lower half of a bearing. Notice how the wear marks are even across the width of the bearing. In this case, the bearing was probably subjected to slightly more load than was intended. Again, here is normal wear on a bearing. However, notice how the wear marks are slightly angled across the width of the bearing. In this case, the bearing was probably subjected to a minor twist condition. Here is heavy wear on a bearing. Notice how the wear marks are not at the bottom of the bearing. In this case, the shaft was probably forced in a sideways direction, potentially from a running shaft misalignment condition. The other most commonly used bearing in rotating machinery is a rolling element bearing, also called an anti-friction bearing. A rolling element bearing consists of an inner race, spherical, cylindrical, or barrel-shaped rolling elements, an outer race, and a cage. Typically, the outer race is stationary and the inner race rotates. If a load is applied in a specific direction as shown in the illustration, at any point in time, only a few of the rolling elements are actually supporting the load in the bearing. This area is known as the load zone. As the shaft rotates one by one, each rolling element moves into the load zone where the lubricant is squeezed to a very thin film and the pressures are the highest. If the direction of the load changes, so too will the load zone. Now, bear in mind that even on horizontally mounted shafts, it is possible for the load in a bearing to be in the upwards direction. Because the load on this type of bearing is concentrated in a few small areas where the rolling elements are closest to the raceway, the oil film is very thin, in some cases near 1/1,000,000th of an inch. The greater the load, the thinner the film thickness. If a piece of rotating machinery is running at 1800 RPM, in a 24-hour period of time, the shaft will rotate over 2.5 million times. I sure hope a dirt particle doesn't try to pass between any of the rollers and the raceway in a day, or a week, or a year. I wonder what the chances are of that happening. I wonder how long a bearing is supposed to last anyway. There seems to be a relationship between how long a bearing lasts and the load imposed on a bearing. This statistical relationship is called the L10 life or B10 life or rating life. Every bearing has a basic load rating shown in the rating life equation as the variable C. Some bearings are rated to carry 100 pounds of load, others 500 pounds of load, and others several thousands of pounds of load. A bearing might have a basic load rating of 100 pounds, but what is it actually seeing? 10 pounds, 100 pounds, or 200 pounds? The actual load that a bearing is subjected to is expressed in a rating life equation as the variable P. The L10 term is expressed in numbers of revolutions, usually in the millions, that will occur when 90% of its life is gone with just 10% of its expected life remaining. To statistically determine the life of a bearing, you take the basic load rating of a bearing, divide it by the actual load it sees, then multiply that number by itself 3 times. Mathematically, that's very interesting, but what does it mean in the real world? If you had, for example, a bearing running at 1800 RPM with 100 pounds of load on it, and let's say that it would statistically last for 10 years. If you then took an identical bearing, placed 100 pounds of load on it, and ran it at 3600 RPM, statistically that same bearing would last for only 5 years. If you took yet another identical bearing, placed 200 pounds of load on it, and ran it at 1800 RPM, statistically that bearing would only last for about 12 to 14 months. In other words, if you double the speed of a bearing that is subjected to the same load, you cut its life in half. However, if you double the load in a bearing, you don't cut its life in half, you cut it by a factor of 8 to 10. If our goal is to increase the operating lifespan of our rotating machinery, then it seems logical to conclude that the most effective way to do that is to reduce the forces on our bearings, right? Which brings us to the following question. What kinds of things will put loads on our bearings and shafts? There are 2 basic types of forces that act on our rotating machinery: static forces and dynamic forces. Static forces are forces that act in one direction only. Dynamic forces are forces that change their direction or decrease and increase in intensity on either a periodic or a random basis. By definition, static forces always act in one direction. These forces will diminish the oil film thickness in the bearings, increasing the possibility of foreign object damage as undesirable objects pass between the shaft and the bearing, or between the rolling elements and the raceways. With diminished oil film thickness comes increases in friction, resulting in oil and bearing temperature increases. A classic example of a static force is the downward force on a bearing due to the weight of the shaft. Designers of rotating machinery know the weight of the rotors and size the bearings accordingly. They do put a factor of safety into the shaft and bearing design, but they don't anticipate that the forces will be 2 to 3 times higher than gravitational loads. Another example of something that puts static forces in a bearing is belt tension. Keep in mind that the bearings on the motor and fan are seeing forces from 2 different mechanisms on belt-driven machinery. Not only are the bearings seeing the downward force due to the weight of their shafts, but now an additional force from belt tension is present. It should now be apparent that our bearings can be subjected to multiple forces at the same time. Another classic example of a situation that will produce static forces on bearings is the shaft misalignment condition. These are 3 very common sources for loads on bearings. Also be aware that static forces are continually present, whether the machinery is running or not. Once a drive system is started, other forces start to appear. Forces that are periodic and repetitive in nature are defined as dynamic forces. Forces that are sporadic are transient forces. The most prevalent forces in operating rotating machinery are the dynamic forces. A classic example of a dynamic force is an out-of-balance condition. At some point on a rotor, a heavy spot may exist. The instant rotation starts, the heavy spot changes its angular position and begins producing a centrifugal force. When the heavy spot is in the 12 o'clock position, the centrifugal force is in the upward direction. When the heavy spot is in the 3 o'clock position, the centrifugal force is toward the right. When the heavy spot is in the 6 o'clock position, the centrifugal force is in the downward direction. When the heavy spot is in the 9 o'clock position, the centrifugal force is to the left. Even though the frames and casings of our machinery are fabricated from metal, metal is elastic and will deflect when a force is applied to it. Since the direction of the force is continually changing, the elastic support that is trying to hold the shaft in a stable position is responding to the centrifugal force acting on it and consequently deforms elastically. This repetitive elastic deformation from the circulating centrifugal force is referred to as vibration. Another example of something that can cause dynamic forces is an eccentric sheave. Notice that the sheave on the fan shaft is off-center. When the high spot on the sheave is in between the motor and fan shafts, the belt tension decreases slightly. When the high spot on the sheave makes a 180-degree rotation, the belt tension increases slightly. This variation in belt tension force produces a dynamic force, which in turn causes vibration to occur. Also be aware that the fan rotor could be out of balance, and the angular position of the heavy spot may not be in the same angular position as the high spot on the sheave. Additional vibration could occur from damaged bearings, damaged belts, or a myriad of other sources. What is vitally important to understand is that the only types of forces that can cause vibration are dynamic forces. It is also vitally important to remember that dynamic and static forces can exist at the same time. Returning back to our list of the symptoms of shaft misalignment, you might also notice higher bearing temperatures or higher than normal discharge oil temperatures. Another symptom is excessive amount of lubricant leakage at the bearing seals. Another symptom of shaft misalignment is that certain types of flexible couplings will get hot when the drive system is running. Around 1991, two technicians at a beverage manufacturing facility in California ran an extremely interesting and revealing experiment. When these two mechanics started a maintenance quality improvement program which included precision shaft alignment, they were met with some opposition and ridicule from their coworkers. We've been aligning all the machinery up to now with our eyeball and straight edge, and we can get the alignment down to within 40 or 50 mils that way. Why do we need to get it any better than that? The coupling will take care of that small amount. If you think we're going to change, prove to us otherwise. Good point. Where's the proof? When I went out for a training class at the plant in 1990, I mentioned to these two technicians that some flexible couplings will get hot when misaligned, and they got a little curious. Shortly after that, Frank and Bruce got a 10 horsepower electric motor and a 10 kilowatt electric generator and mounted them to a frame. They then went to their spare parts storage, got 6 different flexible couplings they were using on their rotating machinery in the plant, and mounted them one by one to the motor and generator. They started off by carefully aligning the shafts to near perfect alignment conditions, started the motor up, ran it for 15 minutes, got their new infrared thermal imaging camera, and took a thermal image of the coupling. They then shut the motor down and let it cool back down to ambient temperature. They then loosened all 4 of the motor bolts, installed 10 mils of shim stock under all 4 feet, and tightened the bolts back down. The motor was again started, ran for 15 minutes, and another thermal image of the coupling was taken. This process was repeated several times, where they kept adding 10 more mils of shim stock under all of the motor feet. In some tests, they installed 30 total mils of shims, and on other tests, they installed up to 40 mils of shims. After one coupling was ran through all the varying amounts of controlled intentional misalignments, that coupling was removed and a different one was installed for that coupling's battery of similar test runs. Here is what they observed. Here are 2 of the 6 couplings that were tested: a jaw-type coupling and a rubber tire-type coupling. On the far left is a regular photograph of the flexible coupling with the generator on the left and the motor on the right. The middle image is the thermal image of the coupling when it was extremely well aligned. To the right of that is the thermal image of the coupling in its most extreme misalignment condition, and on the far right is a graph showing what happened to the temperature as the motor was misaligned 10, 20, 30, and in some cases 40 mils. As you might suspect, the black areas on the thermal images show low temperatures, the orange areas are warm, the yellow areas are hot, and the white areas are very hot. What's interesting is, notice what's getting hot on the couplings. It's the flexible elements. Here are 2 more of the couplings that were tested. Again, notice what is getting hot in the coupling. In the rubber gear coupling, it's the rubber insert. Notice, too, that the Magnaloy coupling hub on the motor is much hotter than the coupling hub on the generator. That's kind of interesting. Several years ago, a colleague of mine from a steel manufacturing facility who gave me another thermal image of a misaligned motor and pump showed that the pump coupling hub was hotter than the motor coupling hub. And here are the other 2 couplings they tested: a metal ribbon coupling and a chain-type coupling. Keep in mind that these shafts weren't misaligned a 1/4 of an inch. This increase in temperature was occurring with as little as 40 mils of misalignment, right within the accuracy capabilities of a human's eyesight using a straight edge. I don't know, what does it look like to you? Can 30 or 40 mils of misalignment make a difference? Sure looks like it to me. The data that was collected by these adventurous individuals eventually was published in several maintenance periodicals in 1992. In the articles, the statement, "all flexible couplings will get hot when they are misaligned," appeared as one of the conclusions to the experimental study. That all-encompassing statement is not really true because one design family of flexible couplings wasn't tested, and that type of coupling typically won't get hot under misalignment conditions. So we better take a look at some basic information on flexible couplings to help us understand what's going on here. There are dozens of flexible couplings, but to a certain extent they fall into 3 basic design families: mechanically flexible, elastomeric, and disc or diaphragm. Here are some examples of mechanically flexible couplings: chain couplings, metal ribbon couplings, gear couplings, and the grandfather of all couplings, the universal joint, all are considered as mechanically flexible couplings. All mechanically flexible couplings require some sort of lubrication to survive for prolonged periods. When operated under misalignment conditions, these couplings will generate heat through sliding friction as the chains slide back and forth across the sprocket teeth, or the external gears on the coupling hubs slide across the internal gear teeth on the sleeves, or the metal ribbon slides across the slots in the coupling hubs. That's why the chain and metal ribbon coupling were getting hot running under a misalignment condition, as you saw in the previous slide. Here is another design family of couplings. These elastomeric type couplings use some sort of flexible yet resilient material such as rubber or plastic to accommodate a slight misalignment condition. Examples here show rubber tire type couplings, rubber insert couplings, and rubber gear type couplings. These couplings do not require any lubrication like mechanically flexible couplings do. But if you remember, the first 4 couplings you looked at in the misalignment study a few slides back were all elastomeric couplings, and the elastomer was getting hot. Now, what would cause that? Well, in the case of the elastomeric insert coupling shown in the upper right, lower left, and lower center photographs, they are getting hot for the same reason as a mechanically flexible coupling, sliding friction. In the case of the rubber tire type coupling, whenever you cyclically twist or shear a material, you begin generating heat through molecular friction. And yet here is another design family of flexible couplings. These couplings also do not require any lubrication. These are disc or diaphragm type couplings. A metal disc or contour diaphragm elastically bends to accommodate slight misalignment conditions. There isn't any sliding of one part against another, so no heat from sliding friction is generated. Indeed, the metal discs are elastically bending and producing some molecular friction, but nowhere near the amount of molecular friction generated in elastomeric type couplings. So the statement that all flexible couplings will get hot when subjected to misalignment might be true for mechanically flexible and elastomeric couplings, but it is not true for disc or diaphragm type couplings. Continuing on with the list of symptoms, similar or spare drive systems seem to be able to operate for longer periods of time before maintenance is required. There seems to be more frequent coupling failures. In moderate to severe misalignment conditions, the shafts are cracking or breaking from high cycle fatigue. With mechanically flexible couplings, there is grease or oil on the inside of the coupling guard and on the base plate. Another apparent symptom of misalignment is loose foot bolts or loose shim packs or loose dowel pins. This is usually attributed to a sawfoot condition, which will be discussed in detail in another tutorial. If we were trying to align a motor and pump and had, let's say, a ½ inch of misalignment between the two shafts, and installed the coupling, if the machine cases were transparent and we could see the shafts inside the machines, we would observe the shafts elastically bending in an S-shaped curve. Please do not misinterpret this drawing. The shafts are not permanently bent, they are just elastically bending. I understand that the flexible coupling is designed to flex to accept a slight to moderate misalignment condition, but there is a limit to the amount of misalignment a coupling can withstand. When the limits of a coupling's misalignment capacity is exceeded, then the shafts are going to have to elastically bend to accommodate the excessive misalignment. When this occurs, internal clearance changes inside the machine where you could begin to see uneven air gaps in motors, bearing seals begin to rub, gears begin meshing improperly, impeller to stator clearances in pumps are altered, mechanical packing in pumps start to leak, or the rotating and stationary parts of a mechanical seal are not concentric. In addition, the loads on the bearings are increased and on some bearings decreased to the point where the shaft becomes unstable, producing a whirl condition. Because the shafts are elastically bending, the possibility of cyclic fatigue failure is increased. The other major thing that people do not realize is that this illustration shows why you should never keep a coupling engaged when attempting to align machinery. In conclusion, there are 4 ingredients needed to align machinery successfully: training, tools, time, and, most importantly, inspiration. For a rotating shaft to be stable, it must have 2 radial bearings. For a shaft to keep from moving axially, it must have a thrust bearing. There are 2 basic types of bearings used in machinery: sliding type bearings and rolling element bearings. There is no way a pump is going to rotate without help, and there is no sense in running a motor all by itself, so we need to connect drivers like motors, steam or gas turbines, and diesel engines to the machines that we want to operate to make our process work, such as our pumps, compressors, generators, fans, and all of the rest of the machinery that gets your product to market. To connect our drivers to our driven machinery, we mechanically join them together with flexible or rigid couplings. We discussed that there is a possibility that the shafts of our drivers and the shafts of our driven machinery can be misaligned, and that the coupling that connects these shafts together attempts to accommodate a misalignment condition, but there is a limit to the amount of misalignment it can accept. Once that limit is approached or exceeded, the shafts begin to elastically bend. Determining what acceptable alignment tolerances are will be discussed in another tutorial. You know, I often hear people telling me that they have bearing failure problems, seal leakage problems, coupling problems, and occasional shaft failures, but they never have any alignment problems. Is it possible that they are confusing their symptoms with the real cause of the problems? Experience has shown that one of the major sources of these symptoms is shaft misalignment. What better time is there to learn how to do this than right now? And what more qualified person is there to do this than you? Hey, thanks for your interest, and I hope you continue with this training series.